Okay, to start the next unit, we are going to do a tiny little bit of exponent review, and then we'll introduce some new exponent rules you didn't see last year. We have some definitions to start off with. Here, if we have something that is x to the m, the entire term that's here, x to the m, this is what is referred to as a power. The x from the power is what is referred to as the base, and the m part there, that is the exponent. Okay, so we're going to be using that terminology as we move through this. So the exponent laws on this side are ones you should have seen in the grade 9 course. So the first rule says that if you have powers of exactly the same base and they're being multiplied, even though there's no kind of explicit sign that says multiply when we have terms that are right beside each other, there's an implied multiplication. So here I've got powers of the same base that are being multiplied, then we keep the base and we add the exponents. So I have an example here. Here I've got powers of the same base, they're being multiplied, so I'm going to keep the base, add the exponents. So this is an x to the 5. Here, same type of thing. If I have powers of the same base and they're being divided, then the rule is to keep the base, but now subtract the exponents, so that same thing's going to happen here. This would be an x to the, since I'm dividing to the exponent, that's 5 minus 3, so this would give me an x to the 2. If I have a power that is raised to an exponent, then the rule is to keep the base and then just multiply the exponents together. That's what this is saying when they're right beside each other. So here if I've got x cubed that is raised to the exponent 2, then this is an x to the 3 times 2, so this is going to be an x to the 6. Okay. If I have a power where the base is made up of multiple, variable parts being multiplied, like here I've got an x times y, then that exponent applies to both of these. Okay, so here I've got an x times y to the 3. That means this is the same thing as the x getting cubed and the y getting cubed, and they're still getting multiplied. And the same thing happens with division. If you want to think of it like a fraction, that's pretty much the same thing. Then that exponent that's here is going to apply to both the numerator and the denominator of the fraction, or both parts of the division. So here this is going to be an x squared over a y squared. Okay, we've got a few other examples on the side we can work through with these rules. So here I've got some powers of the same base, but I also have some coefficients. And with coefficients, what we could do is, because we are multiplying, we can multiply numbers and variables in any order. The order in which you multiply never makes a difference. So what I can do is just say I'm going to multiply the numeric parts together, and then I could multiply the variable parts together. And if I multiply the variable parts together, then I'm using this exponent rule, which says powers of the same base being multiplied, just add the exponents. So this is going to be an x to the 5. Okay. Here I've got powers of the same base. Even though I don't have variables, it doesn't really matter because the rule still works that way. Here if I've got 7 to the 6 divided by 7 and there's an implied 1 there, the rule is to keep the base and then subtract the exponent. So this would be a 7 to the 5, and then you can evaluate that. Same kind of thing here. Even though there's no variables, the exponent rule still works. Here's a power raised to an exponent, so this is keep the base and then multiply the exponents. Here for this, if you see our terms made up of kind of multiple parts, this is saying this rule that this squared that's on the outside, the exponent 2, needs to apply to everything. So this is the same thing as saying 5 squared, x cubed squared, which means it's now going to use this rule also, because it's a power raised to an exponent, so this would be an x to the 6, and then y to the 4 squared, so it's using this rule again, y to the 8. Okay. And the last one here, there's a couple of different ways of doing it. I'm just going to follow BEDMAS, which says I should simplify inside the bracket before I do the exponent. So if I do that, then think of this kind of part by part. I'm going to do the numeric parts, the coefficients, then I'm going to do the a's, then I'm going to do the b's, and I'm going to try and use these rules up here as much as possible to do powers of the same bases. So here if I do a 16 divided by 4, that is a 4. Let's write that a little bit better. And then I've got an a to the 3 divided by a to the implied 1, so it's a division, so we're going to use this rule, which means keep the a, and then 3 minus 1. And then b to the 5 divided by b to the 9, it's another division of powers of the same base, so this is a b to the 5 minus 9 is a negative 4. And then we're squaring the whole thing afterwards, which means now everything inside here, it's one big monomial, it's one big term, so everything gets squared. The 4, the a squared, the b to the negative 4, and it's using this rule, number 4, which means this is going to look like 4 squared, 16, a squared squared, rule is to multiply exponents, and then b to the negative 8, and we'll see in a second how we deal with that negative exponent. Okay, on the other side of this, let's flip this over. We're going to be looking at two new rules you probably didn't see in the grade 9 course. 0 and negative exponents. So they've given us a little investigation that we can kind of work through. Here, if you notice, these are all powers of 2. So if I wanted to, let's say, do 2 to the 4, this just means 2 being multiplied 4 times. So if I did 2 times 2 times 2 times 2, this is going to be a 16. And if I do 2 cubed, this is an 8. 2 squared is a 4. 2 to the 1 is a 2. And if you notice the pattern that's happening here, as I keep going down by one exponent each time, look at what I'm actually producing. I went from a 16 to an 8 to a 4 to a 2. Each time as I go through this pattern, I'm kind of cutting the number in half. I'm dividing it by 2. Which means if I follow this pattern without even really paying attention to this side, and I keep splitting it in half, then if this is a 2, then the next one's going to be a 1. I cut it in half. And then the next one would be half of that. And then the next one would be half of that, and I can keep cutting it in half. And the same kind of thing here could happen for the 3's, and then we can generalize. 3 to the 4 is an 81. 3 cubed is a 27. 3 squared is a 9. 3 to the 1 is a 3. And then the rule here, if you kind of look at the pattern that's happening, all these keep getting divided by 3. So then the next one would be a 3 divided by 3 is a 1. Then divide by 3, divide by 3, divide by 3, divide by 3. Okay, now if you notice here, a couple of things. First, the exponent that's a 0, both of these are exactly the same, and that's kind of a general rule. Anything to the exponent 0, automatically going to be a 1. Okay, which means here if I follow some of these examples, there's a whole bunch of stuff going inside this bracket, but the entire bracket's raised to a 0, which means that this entire bracket is going to be a 1, and then the 3 is getting multiplied in front of that, so this is just going to be a 3. Here I've got a negative 21x to the 4 to the 0, which means everything in this bracket is raised to a 0, so this is going to be a 1, but that negative wasn't part of the bracket, so it just gets carried down. Okay, now with negative exponents, if you look at what happened here, 2 to the negative 1 was a 1 over 2, 2 to the negative 2 was a 1 over 4, 2 to the negative 3 is a 1 over 8. Well, these are really similar. The 2 to the 1 and the 1 to the 2, these are reciprocals of one another. 2 to the negative 2 and 2 to the positive 2, they are also reciprocals. A 1 over 4 and a 4, a 1 over 8 and an 8, and a 1 over 16 and a 16. So our general rule is that when you have a negative exponent, all this really means is that it's the reciprocal of whatever the positive exponent is. And what that means is it's just 1 over that number. So here our general rule, x to the negative m, this is automatically going to be 1 over whatever x to the positive m is. And you can kind of see that over here. So if I had 3 to the negative 1, that means that this is 1 over whatever 3 to the 1 is. 3 to the negative 2 is 1 over whatever 3 squared is. 3 to the negative 3 is 1 over whatever 3 cubed is. And 3 to the negative 4 is 1 over whatever 3 to the 4 is. So if we use this for these examples, 3 to the negative 2, this is 1 over 3 squared, which is going to be a 1 over 9. And then here with these addition, this is kind of preventing us from using a more kind of elegant rule. I'd have to do this one separately, so this is a 1 over 4 squared, plus I would have to do this one separately, this is a 1 over 2 to the 1, and then just work out what each one of those is. So this is a 1 over 4 squared is a 16, plus half, and then get a common denominator, and I don't really like writing along a line, it's not proper, so I'll just write below this. This is a 1 over 16 plus common denominator here would be an 8 over 16, so this is a 9/16 if you do that. Okay, with a couple more of these examples down here, 7 to the negative 3, this is a 1 over 7 to the 3, which if you evaluate it is 1 over, what is that, a 343 I think? And we'll double check that. Okay, here if I have a 1 over 2 to the negative 1, this means a couple of things. This is 1 over whatever 1/2 to the positive 1 would be, which if you remember, all that fractions are divisions. So anytime I see this, if you want to, you could rewrite it as 1 divided by 1 over 2. And how we divide fractions is we multiply by the reciprocal. So this is 1 times 2 over 1. So this is just a 2. Or a nice little shortcut you have with these negative exponents, whenever the base of the power is a fraction, what that negative means is we need to take a reciprocal there. So what I could do is use the negative here and say, let's flip this, and I've used up that negative. I still have the 1, but I'm using the negative to flip it back, and now it's 2 to the 1 to the 1, which just means it's a 2. We'll do C because this is a little bit easier to see here, that if I have 3 over 4 to the negative 2, this, if I use the negative, is going to flip the base. And notice I'm not writing the negative now anymore because I've now used it to flip the base to become a 4 over 3, and now that 2 applies to both of these. It applies to the 4, so 4 squared over 3 squared. There. Here's another one of those like up here. I have to do them separately because there's not multiplication but a subtraction here. So this is a 1 over 2 to the 1 minus 1 over 2 to the 2. So this is a 1 over 2 minus 1 over 4. And then getting common denominators, I'm just going to get a 1 over 4 out of this. Okay, with the 2a, there's a couple of different ways we can do this. What I think I'll do is I'll work with the numerator, and I'll simplify that. So here what I'm going to do is similar to what we did on the other page, is this is kind of one big term being multiplied by another one big term, monomial times monomial. I'm going to multiply the numeric parts together, the coefficients. So 12 times 5 is a 60. I'm going to multiply the m's together, so powers of the same base being multiplied. Keep the base. Add the exponents, so 5 and a negative 11 is a negative 6. And then the n's are getting multiplied, so powers of the same base. We multiply, we keep the base, add the exponents, negative 2 and a 6 is a positive 4. And I didn't do anything with the denominator yet. I'll do that in the next step. Don't need to do everything all at once. And now I've got the same kind of setup going on, but now it's division. So I could divide the numeric parts, the coefficients, so that'll give me a 4. I'm going to divide these powers of m, which means keep the actual base and subtract the exponents. So negative 6 minus 3 is a negative 9. And then for the n's, keep the base, subtract the exponents. Be careful, 4 minus negative 4. So because I'm subtracting a negative, I'm actually adding. This is the positive 8. Okay, Now we have this one thing that has a negative exponent. The 4 doesn't have a negative exponent, it's a 4 to the 1. The n doesn't have a negative exponent, it's an n to the positive 8. Only the m does. So one thing you can do with these negative exponents is remember they're just reciprocals, which essentially means they're on the wrong side of the fraction. So a proper way of writing this very last one would be to say this: keep the 4 where it is, keep the n to the 8 where it is, but move this one to the denominator. And then rewrite it with a positive exponent. Because that's essentially what these negative exponents are doing. They're moving things to the other side of the fraction. And then same kind of thing over here. I've got all this stuff to the 0, so that's going to be a 1. Anything to the 0 is a 1. Minus, here's a fraction to a negative exponent. So let's flip it. And rewrite it with a positive exponent. So that means that this is just 1 minus 3 over 2. So let's get some common denominators. And we're done.